Chapter 4, Part 3, Nomenclature of Cycloalkenes, Polyenes, and Molecules of the Day. The nomenclature of cycloalkenes uses all the same rules as cycloalkanes, except again, the alkene is the priority item. It's automatically number 1. If you do end up having to number an alkene, the numbering must go across the alkene. And make sure that you use the EN infix. So, for example, in this first molecule here, there's nothing else on this molecule. There's only one possible place that the alkene could be. So this one is just simply cyclohexene. So let's break that down again in case you've kind of forgotten. We use hex because that prefix means 6 carbons, and there are 6 carbons in this ring. We're using the EN infix to show us that there is a carbon-carbon double bond. We're using the E suffix because this is just a hydrocarbon. And then cyclo tells us that this is a ring. So next one, we have a methyl group on here, and we have the alkene. Now this is where we have to follow that rule. Numbering must go across the alkene. So by across the alkene, we mean that your numbering system has to go through the alkene. So you can go 1 to 2, but you cannot go 1, 2, 3, 4 this way because my consecutive numbers do not go across the alkene. So I want to start numbering here because otherwise my only other numbering system that goes across the alkene would be 1, 2, and this methyl group would end up a much larger number. So I'm starting here so that my methyl ends up on carbon number 3. Now I don't have to say that the alkene is on carbon number 1 because that's assumed. The only time that you have to indicate the carbon number of the alkene in a cycloalkene is if there's multiple alkenes or there's something else taking up a larger priority that you have to give the number 1 to. And then at that point you would have to say what number you ended up giving to the alkene. So this is a derivative of cyclopentene, and we have a methyl on carbon number 3. So this is 3-methyl cyclopentene. On this next example, we have our alkene here. So our question that we have to ask ourselves is, do we want to start here and go this way for our numbers? Or do we want to start here and go this way? By starting at this carbon, we are also giving the number 1 to the methyl, and then that would be 1, 2, 3, 4 ethyl. Our other numbering scheme that could be possible would be 1, 2, 3, 4, 5. So we end up giving the numbers 2 and 5 to our substituents. That's definitely not better than 1 and 4. So we're going to go with our first plan. 1, 2, 3, 4, and then just for fun, 5 and 6, even though there's nothing on them. So we have 2 substituents. We have an ethyl group on carbon number 4, and we have a methyl group on carbon number 1. We're going to alphabetize them. So that is 4 ethyl, 1 methyl, cyclohexene. And that's our name. Next up, we have dienes, trienes, and polyenes. So these are molecules that have multiple alkenes in them. All of my examples here are dienes. So when you're naming a diene, you are going to have to use some numbers to indicate where that alkene is. So in our first molecule, we have 2 alkenes. They're both on the last or first carbons. So it doesn't matter where we start. This molecule is symmetric. So 1, 2, 3, 4, 5. So we know that we're going to use the prefix pent. So anytime that we use di, tri, tetra, etc. to indicate multiple of something, we always put that directly in front of the thing that we have multiple of. So we have 2 alkenes, so we want to put the di directly in front of ene. But that gives us a little bit of a tricky thing. That would be pentdiene, And the IUPAC system does not want us to have this consonant clash here. And so you have to add an A. So it's pentadiene. So this tells us that we have 5 carbons in our chain. We have 2 alkenes, and it's a hydrocarbon. And then the A is just there to make it sound better. And then we also need to indicate the numbers that our alkenes start on. They start on carbons number 1 and 4. So this is 1, 4, pentadiene. And remember, we separate numbers with commas, and we separate numbers from letters with dashes. In our next example, we have a 4-carbon chain that has 2 alkenes, and we have a substituent on one of our carbons here. So if there were no substituent, it wouldn't matter which side we number from. But since we do have a substituent, we want to number closest to that substituent since the alkenes are in the same locations. So we have carbon number 1, 2, 3, 4. So we know that this name is going to start with 2-methyl. And then we have 1, 3. And then we have bute because we have 4 carbons. And then again, we have that T before where our diene would be. So this is going to be butadiene. Sorry, that came out weird from my pen. Let me try to write that again. Bute, oh, that's worse. Bute. Diene. Okay. Butadiene. Butadiene. Okay, in this next example, we don't have any substituents or anything, but it is cyclic. So we have 5 carbons, and the numbering has to start at the top of one of the alkenes. It wouldn't matter which one you chose. So let's go 1, 2, 3, 4, 5. So our numbers for our alkenes are going to be 1 and 3. So this is 1, 3, cyclo, because it's cyclic. And then here's where that pent, and then we have to add in our fun little A, and then diene. Okay. 1,3 cyclopentadiene. Okay, this last one is the most complicated. I deliberately put the alkenes in the middle of the molecule so that we would have to figure out the E and Z first before we could do anything, and then we'll also have to make it part of the nomenclature. So let's go ahead and number our carbons and just figure out the bulk of the name, and then we can do the EZ last. So we have a substituent here, so we're going to start numbering here. 1, 2, 3, 4, 5, 6. Because the alkenes are in the same positions, so it doesn't matter based on them where we start numbering. So this is going to be 3-methyl, and then we have an alkene starting on 2, and we have an alkene starting on 4, and this is hexadiene. So this is the name of the molecule, 3-methyl 2,4-hexadiene. Now the last thing that we have to do is figure out our E and Z. So let's look at our alkene that starts on carbon number 2 first. So we're comparing methyl to hydrogen. So that methyl, that carbon, is going to win. And then on the other side, we have a carbon versus a carbon. So we're not going to make our decision there. We go out to our next level, and we see that this carbon is attached to a hydrogen, and a hydrogen. This other carbon is attached to a carbon, and there is a hydrogen here, but then there's also a third imaginary bond that we call C star, because 2 of our bonds are actually to the same carbon, but we want to recognize that there are 2 bonds there. So C star is a way of indicating that we have 2 bonds to carbons, just so you're counting your number of bonds correctly. So we're comparing carbon, hydrogen, carbon to hydrogen, hydrogen, hydrogen. So that means that our carbon, hydrogen, carbon is going to win. So our alkene starting at carbon number 2 has the high priority groups on either side of the alkene. So this is an E alkene, 2E. So I'm gonna write that off to the side just as a note, because I'm gonna have to erase all this. So I can do carbon number 4. So this is looking at this alkene that starts on carbon number 4. And this one's a little more clear because we have 2 hydrogens attached here. So it's pretty obvious that our high priority groups are this, and they are trans to each other, so that would be E. So to add the E's into our name, we're going to write 2E, comma 4E. Put it in parentheses and then put a hyphen. So parenthesis 2E, comma 4E, close parenthesis, hyphen 3, hyphen methyl, I guess I usually say dash, dash 2, comma 4, dash hexadiene. So that one's quite a mouthful, but that's how you do it. Okay, this last slide is an example of a molecule of the day. I try to scatter these in as we get into more and more interesting functional groups. I'm never going to quiz you over these. I don't test you over these. The entire purpose of the molecules of the day is just to provide some sort of context for the material that we're learning. I think sometimes, especially when we're taking a class like this, where I don't think any of you have any intentions of ever, working in an organic lab, which is totally fine. I know that you're wildlife biology majors, your nutrition majors, clinical sciences, a million other things. So I want to bring it somewhere that you care about, biology moment. So this molecule here is beta carotene. You can tell that this is a polyene. I had to count the carbons earlier because I was trying to draw this out for you. And I believe there were 18 carbons in this chunk here. So that's 9 alkenes just in this part alone. Actually, 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah. And then there's 2 more here. So there are 11 alkenes there. That's quite a lot. This is beta carotene. This is the red-orange pigment that is abundant in fruits and vegetables that are also red or orange, such as carrots. This is a precursor to vitamin A. Now, when we eat these vegetables, our bodies take that precursor, and using the oxygenases, the enzymes in our body, it is broken into smaller molecules. This one is called retinol, and this is one major form of vitamin A. This next molecule is what happens if you oxidize retinol. You end up with retinal. This is the chemical basis of animal vision. This is bound to opsins, which are the proteins in the photoreceptor cells of the retina. So this is why for a long time people believed that if you eat carrots, it could improve your eyesight. Turns out that's just wishful thinking, but this is where that idea came from. Now, one other thing that I want to point out here that we haven't really learned yet, but we kind of have learned this a little bit, is there's some fun nomenclature here. So this is an alcohol functional group. Notice the ending of this name. Even though this is not an IUPAC name, this is a common name given to a much more complex molecule that would have a truly wild IUPAC name. Notice it has this OL ending, which is the ending that we use for alcohols in IUPAC nomenclature. And then when the only change to this molecule is taking the alcohol and oxidizing it into an aldehyde, it's given the suffix that we use for aldehydes, which is AL. So retinol is oxidized to retinal. So that's just a fun IUPAC nomenclature moment snuck into your biology moment.